Now, the thing is, this is a program. This is a program. Let's say the program is called email. Okay. This can have multiple processes. Okay. Process 2, process 1, process 3. This can have multiple processes. One email program can be used by different users, also different processes. Okay. Now, a single program, if a single program can have multiple processes, how can we differentiate it? How does keep track of which process is what? The question is, how does OS keep track of which process is what? So that is why we have an entity called PCB, process control block. And again, imagine this entity as a container, and it has some components. First of all, PID. We talked about PID a little bit when we spoke about fork and execution fork and exec in system calls. And we have program counter, we have process state, we have registers. Now, this is super important. A list of open files and other things. So these are the necessary things we are going to look in this topic. So it's a numerical value given to the process to identify. First of all, I think here itself a good amount of work is done. Now we have way to differentiate. This process is different from that. So this is a process, this is a parent, and this is going to fork into two child one, child two, and this is PID 0, PID 1, PID 3, something. Huh? Now this child can go out and talk to other nodes, PID 33, something. Uh, and once the work is done, this can go back to the parent. So like this, we have a way to differentiate. Now, what's a program counter? Uh, in the above process, in the components of process, we looked at a, a section called text. Where is it? It's the section called text. Now, this text works with the program counter, but how? Program counter, it indicates the address of the next instruction. So let's say this is a text. There are multiple lines of code, and let's say then if program counter is equal to 5, so 0 1 2 3 4 5, so the next address of this instruction is this. So all this is executed, and this will be executed now. This will be executed now, and this instruction is not will not be in a linear mode. Sometimes it will jump to instruction one. Otherwise, there will be a loop in instruction two. This doesn't flow in a linear fashion. So this program counter and process state. What's a process state? So this is a disk. There will be a pool of programs here, and this goes to ready. It's a queue. Okay, let's say imagine this is like this. All the programs will be arranged mm, in a queue fashion. Program 5, program N. Okay, this is a ready queue, And here, this ready queue will go to run, which is nothing but CPU. This program one will given a chance to utilize the CPU to do some computations. And when this is done, now program one is here. And when this is done, this will terminate. So all is ready, run, terminate. Sometimes it will get blocked. Okay, blocked. And again go to ready queue. All these states is called a process state. A process will not only just go to run, not only will be in ready, it will travel everywhere to get the computations or get the required instructions to be done. So the next is the CPU registers. Now we have done this and this. Yes, we are going to look at registers. We looked at process, right? We looked at process. There is data, there is stack pointers, program counters. All this is there, and there are other elements also. Let's say this process one, this is process one. Some kind of computation is going on. Now this is going to get blocked. We know that the process state can be blocked. It is definitely possible. Although we don't know for what reasons it is getting blocked. But right now, just try to imagine suddenly this is going to get blocked. Now, what happens is compute CPU will have some registers. Okay, it's called accumulators. Maybe I'll write it above. Accumulator, stack pointers, general purpose registers. Okay, there are registers. Registers is again uh, a memory unit which is faster than RAM actually, because it's closest to hardware, and it is also damn expensive. So this data will be given to accumulator probably, or the stack pointers will go to stack pointer register. This program counters, which keeps tracks of what instruction should be executed next. That numerical value will go to general purpose registers, and the other things, other general purpose registers. So every data of this process one will be given to the registers, and this will be taken out. Now this will exit. Again, process 2 will come. Hmm. So based on this PID, P process ID, all those data that is saved in registers before, okay, it will be loaded back again. Now this will loaded back again for process 2. So like this, now we have a way to take a process out of its execution, like preemptively, in a sense, without completing the whole execution. We can remove it in the middle and we can put some other process, uh, and we can continue where we left off. Again, this process is, oh, I need input output resource, but it's going to take some time. So I'm also going to get out. I'm going to get suspended or sleep for some time, and the other process will come. And the information in the registers will enable the next process to run. So this is what registers do. So like this information must be saved when an interrupt occurs to allow process to be continued correctly afterward. I think one of the biggest hindrances in creating like these operating system, the hardware only understand numbers, nothing more than it. So you have to design it in a way where everything has to be communicated numerically. So that is why we have all these design intersections. Now, if we have to put this in a neat diagram, maybe we can do this. So this is an execution line, and this is process one. Let's say this is process two. This is another execution line, and this is OS. Okay. Yeah, this is OS. So some interrupt is happening here. Okay, interrupt for process one. So now this process one has to go out. What happens is uh, save state into registers. Uh, and now now we understand that CPU is idle. What we'll do is uh, we'll 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 load process 2. Save reload. Okay, reload process 2. Now the execution continues. Now whatever reasons the process went out, it got the resource. Now it is coming back. Okay, from here it is going to come again. Now what we are going to do is we have to take this process to out before. So mm, mm, I think this should be the right way. Yeah. Mm. Save process 2 and reload process 1. So from up until here, this was an execution, and here process 1 is idle because process 2 from idle it is going to execute. Again, it becomes idle because this is going to execute. So yeah, this is the idea. And we also have one last PCB component, which is input output status information. It is list of input output devices allocated to the process. All the list of open files. So that is understandable. So now we have a way to keep track of processes. Since we have a way to keep track of where a process or what a process has been doing, and we can now understand the process states. So this is a very simple concept. Although I would advise the student, whoever is watching, to go in detail, I'm just going to give a brief overview of what it is. Let's say process from the disk, the pool of programs again, we are going to put a program here, okay, in ready queue. And if the CPU is free, this is CPU, and if free, we are going to run the program. Sometimes the program will terminate, so we're going to suspend or block. Okay, and when the suspension or block is over, again it goes back to ready queue. but it go back to running again. It has to go to the ready queue because there are a queue that is there, and it should sit in the queue and wait for the OS to allocate it some space. It has to come in line. Uh, that is called dispatching. We learn about it again, and we can terminate. From ready queue, it is possible that you can go to suspend. And it is possible from run to ready. Okay, so now this is the diagram. Right. So let's try to understand this. Which is sure. Okay. Now let's say this is a program. This is a process. This is a process. Maybe I'll differentiate with color. This is a process and one another process. Okay, we have three processes. Now they are in ready queue, and let's say the CPU understand that there are three processes, and the CPU is now it is trying to process it, and let's say this one gets a chance to use the CPU. Now this process is doing something, and it says I need to read a file. Okay, but the thing is the file is not open. Okay, it is shared with some other process that is going on, so now this process has to wait. So instead of keeping the CPU idle, OS immediately puts this in the suspend block and checks there are two other processes. Now the CPU or the OS understand this red process is of priority. Okay, something has to be done very quick. Or uh, among these two, the red processes burst time or the resource is very less. So it understands it is easy to run this. So it puts in the ready. It's a run state. Now this guy have to wait for some time. The blue guy has to wait for some time. The red guy is running. Competitions are made. Some error has happened, and this guy is crashed. Now the OS is trying to understand it. So until then, this is going to get suspended or blocked, and the blue guy is in run. Now he gets a chance to utilize this CPU. The decision that was made here, like who gets to use the CPU, is called CPU scheduling. Okay, that is called CPU scheduling. And so this blue guy, he runs smoothly. Things are done. He'll go to terminate and we'll delete it. So the process is done. The resources used by this process is again given back to OS. Some other process might use it. Now, this process, this gets the file. He reads it again. So he'll go back to ready. Now the CPU understands it. Okay, it is safe to send this person because he got the file and sends to run. From run, he goes to terminate, will kill. Now this interesting thing is happening here. This guy's crashed already. But he's not able to resolve it. He's waited for some time. He did all the things he can do. He's not able to resolve it. We can directly send him to terminate. Okay. And send him to terminate and we can delete it. So this is what process states are. The process uh, it can move from one state to another. Basically, that's the idea. Mm, uh, the state of process is defined in part by the current activity of the process. Okay, so the process can be present in more than one state. So that's a process status. So we understand that process is going to change its states, but what exactly determines the change, right? We have this question. Process is getting changed, but what determines the changes? So now we are going to launch into another topic called schedulers. As the name suggests, it schedules which process to do what. So we have long-term schedulers, we have medium-term schedulers, we also have short-term schedulers. So what does this long-term scheduler do? So this is a disk. There are programs, pool of programs here. This is going to go into what we call as a ready queue. So long-term scheduler LTS, okay, decides which process from the pool is loaded into memory. Okay, multiple programs, let's say program 1, program 2, program 3, up to program N. So this LTS controls the degree of multi-programming. So this LTS, OS is going to invoke LTS only for a long time, for long. Mm, Not very often. I'll put it in this way. Not often. Okay, the uh, frequency of using LTS is not very often. So that is why LTS it is a long-term scheduler. The decisions it doesn't happen very quick. But look at this short-term scheduler. Okay, again it is also called CPU scheduler. We have state, okay, and we have a queue here, and this decides which gets the CPU time, otherwise we call run. So it selects from short-term scheduler. So in this process, so ready to run, this is run by short-term scheduler. Selects from among the processes. Why it's called a process? Why it's called a process here? Because all these are processes. These are the memory. We have already loaded this in the memory that are ready to execute and allocates CPU to one of them. So this is short-term scheduler. Now we have medium-term scheduler. Okay, now what is medium-term scheduler? And this is again, what is this? A ready queue. A ready queue. From ready queue, it goes to CPU. This I hope you are following this. This is partially executed, and we're going to swap out. For for various reasons, we are going to swap out. Okay, partially executed. And we know uh, to swap in and out the processes, we use a thing called process control block, where it will save the snapshot of whatever it is done in the registers. Uh, Again, uh, when it's time for it to swap in, it will reload the partially executed or partially saved uh, details to run again. So swap in and swap out, CPU, it it can terminate, or I'm sorry, input output waiting queue. So this is again another queue. If it gets input output request. So this is maintained by medium term scheduler. So basically, if I have to uh, put running suspend, okay, ready. So this whole thing is done by medium term scheduler.